Hello and welcome to class. Today we're taking a look at differential calculus, part 3, and we're looking at the applications of differential calculus. I'm Uncle Ed. So by the end of this class, you should be able to apply differential calculus to solving rates of change, including gradient, velocity, and acceleration, and also using differential calculus to solve real-life problems. But before we go into that, let's have a quick review of what we've done in our past and previous classes. First of all, calculus is the study of things that change and finding ways to represent these changes in a mathematical way. In differentiating polynomials, the rule says if y equals ax raised to the power of n, then the y dx equals anx raised to the power of n minus 1. Also, for such expressions that look like y equals to, open bracket 2x minus 7 all raised to the power of 5, we can say 2x minus 7 is equal to t. Then y equals t raised to the power of 5. In such cases, we use the chain rule, which says that the y dx equals dy dt multiplied by dt dx. If y equals uv, where u and v are functions of a variable x, then the product rule says that the y dx equals v du dx plus u dv dx. And lastly, if y equals u over v, then the quotient rule states that the y dx equals v du dx plus u dv dx, all divided by v squared. For a comprehensive solution to all these review that we've just done, please check our previous classes on calculus. Alright, what are the applications of calculus? There are quite a number of them. Now, whenever rates are involved, rates that is in relation to time, it is usually possible to use differentiation to solve related problems. So this class considers the use of calculus in gradients, velocity, and acceleration and real-life problems. Okay, so if you go on to study courses in mathematics, sciences, engineering, economics, you'll find calculus to be an invaluable tool. So just get your minds ready for those of you who would like to study sciences. So our first point of call is going to be in gradients. Here is the example. Find the gradient of the curve y equals x squared plus 3x minus 1 at the point where x equals 3, x equals minus 2, and x equals 0. The solution: y equals x squared plus 3x minus 1. Then the gradient function, the y dx is 2x plus 3. So at x equals 3, the y dx becomes 9. At x equals minus 2, the y dx becomes minus 1. At x equals 0, the y dx is 3. Example 2. If we were to find the equation of the tangent to the curve y equals x squared minus 4x plus 3 at the point 3, 1. The solution is thus. If we're given the equation y equals x squared minus 4x plus 3, the gradient function, the y dx, is 2x minus 4. If x equals 3, then the gradient of the curve at the point is 2. The equation of the tangent is y minus y naught, all divided by x minus x naught, which gives us 2. Remember, y naught is 1 and x naught is 3. So if you substitute that and solve it cross multiplying, you're going to have y to be equal to 2x minus 5. Here's a break. Alright, our next application is going to be in velocity and acceleration. So here's an example. Suppose that a particle's distance s meters after t seconds is given by s equals t squared plus 3t plus 5. We can say that the velocity of the particle is the rate of change of s compared with t, that is ds dt. Since s equals t squared plus 3t plus 5, then ds dt equals 2t plus 3. So we'd simply differentiate ds, ms rather. Therefore, at t equals 2, v equals ds dt equals 2t plus 3. So when we substitute 2 into the equation, we're going to have 7. Acceleration is the rate of change of velocity compared with time and is expressed in meter per second squared. Hence, if the velocity is v meter per second after t seconds, then acceleration is given as dv dt, which is the gradient of the velocity time graph. Suppose a particle is moving such that its velocity in terms of t is given by v equals 6t minus t squared, then the acceleration at any time is given by dv dt equals 6 minus 2t. When t equals 3, then dv dt is 0. And finally, on application of differential calculus, when an object is projected into the air, its height s meters after t seconds is given as s equals 98t minus 4.9t squared. So that is s. Find the greatest height to which it rises. The hint for this question is, at the greatest height, velocity is 0. So we're given the equation. Therefore, velocity, which is ds dt, is 98 minus 9.8t, and we equate that to 0. So when we solve that, we're going to have t to be equal to 10 seconds. And next, we substitute that t equals 10 seconds into the original equation to have s, which is the greatest height, to be 490 meters. So here's your home exercise. Ensure you send in your answers as soon as possible. We'll be waiting to hear from you. Have a lovely day.